Hello everyone, and welcome to this video. Essentially, the scope and goals of this project are to develop a celestial mechanics numerical model that is mathematically complex enough to be challenging and to learn something from it. To constrain this rather broad scope, we will focus on trying to build something that is efficient and long-term Keplerian celestial mechanics, on the order of millions or even possibly billions of years with relative accuracy and great efficiency to do it on my own computer. After some research, the clear for very long-term celestial mechanics came to be Wisdom-Hallman. Then, further research on this program, I have found things from Rebound, an open source celestial mechanics codebase on ways to improve its accuracy and also its efficiency, such as using things like symplectic correctors, variational methods, splitting methods, and even something they call a lazy kernel. So we are going to get into all of those things. To derive the Wisdom-Hallman, we start with the traditional in-body Hamiltonian in inertial Cartesian coordinates, with I equaling 0 meaning the central star and the rest simply being the planets. From there, the Hamiltonian is not separable, so we take a different canonical transformation to the heliocentric canonical coordinates. Here we define capital Q to be equivalent to the Qi minus Q0, essentially the distance from the planets in reference to the Sun. The corresponding canonical momentum simply doesn't change, with the exception of the Sun, which is momentum transforms by the expression the Sun's original momentum plus the sum of the momentum of all the planets around it. Then we can define capital M to be the cumulative mass. From here, it is simple to derive the new Hamiltonian in this coordinate system. Here we can divide the Hamiltonian into a Hamiltonian of the Sun, Kepler motion, and the interaction between planets. This is the traditional method, though for reasons we will get into later, rather than using heliocentric coordinates, we will use Jacobian, meaning that the reference is to the center of mass of the entire system rather than the central body. Where the center of mass of our particles interior of the ith particle is r, thus their coordinates become this new r is equivalent to the original r minus this capital R that we have defined. Because the Jacobi coordinates are linear functions of Cartesian, the rest of the quantities, such as velocity and acceleration, change in the exact same way. Momentum changes different, however. We start with our original equation, where momentum is equivalent to the mass times the velocity. But rather than traditional mass, we will use reduced mass, which is explained through this equation below. Using these coordinates, the in-body Hamiltonian instead becomes this new equation, keeping the potential terms in the Cartesian coordinates and only writing the kinetic terms in Jacobian. Next, for the sake of algebra, we will add and subtract this next term. We will just add it and subtract it in order to make the algebra easier to compute and splitting up the Hamiltonians. We can even further split the Kepler term into this equation below, where each Hamiltonian describes the Kepler motion of the ith particle around the center of mass of all interior particles. That's an important thing to remember, interior particles rather than the entire system. After some more algebra, we can split the Jacobian part into two parts. One that can be easily computed in Cartesian, and the other that can be easily computed in Jacobian coordinates. Now that we have three separable equations that are all much easier to integrate than the highly nonlinear one we started with, where h of 0 is the motion along a straight line of the entire system, h Kepler is the Hamiltonian for Kepler motion, and h int is the interaction of particles outside of the ith particle. Essentially, if we have Earth as our ith particle, objects like Mars or Jupiter would all interact with the Earth, slightly perturbing its motion outside of a traditional Kepler orbit. To note, this methodology only works for near Keplerian orbits. In, say, a three-body diagram, this method would be quite unphysical if all three objects have similar masses. Another case would be for moons orbiting planets that are orbiting stars. We can do one at a time, such as the star and the planet, or the planet and the moon, but we cannot do all three, as the moon orbits the planet rather than the center of mass of all interior objects. We do all this splitting because the original in-body Hamiltonian has no analytical solution. Thus, with this new equation, we can approximate solutions on the specific sub-Hamiltonians. Many methods exist, but the method we are developing is obviously splitting, as we have split these Hamiltonians up into smaller parts that become integrated much more easily. Analytical solutions can be found, or near analytical solutions that are easily integrated with relatively small errors and relatively small computational cost. Thus, to create the symplectic integrator, we use operator splitting method. To do this, we start with the familiar Liouville operator. If you're not familiar with this is simply the same as saying that the derivative as a function of time of some function is equivalent to the Poisson bracket of that function and the Hamiltonian. Now, this equation of the Liouville operator looks a whole lot like the ordinary differential equation that has a formal solution that's fairly simple. Because this equation is a differential operator and not a variable, we can do the same thing, except the exponential operator is defined through a different equation, this new equation that we have below, rather than the traditional Euler's number. Here, the key difference is that the differential operator does not compute as traditional variables do. This here is the backbone of symplectic integrators to approximate this non-commutable equation. Using this, we can take our original Hamiltonian in Poisson form to be this equation below, where L of h is equivalent to L of 0, L of kep, and L of int. Here, let's turn these L's into A, B, and C. Then we can add A and B together to make B and turn C into B. Looking at this, the exact propagator is obviously e to the power of h times the sum of a and b. Now, this is a formalized work that is already used in the generic string method. Here we can find this new equation, which is simply the drift-kick-drift, drifting along Kepler motion and the motion of the center of mass, and kicking using the interaction between planets. To add further efficiency, we add an additional method, the symplectic correctors. A symplectic corrector is simply a small adjustment to the coordinates that one does before and after running a symplectic integrator, so that the numerical trajectory more closely matches the real physical trajectory. Because they are only applied at the very beginning and the end, one can arbitrarily add higher order correctors with negligible effects on the speed. We choose an 11th order corrector, as that effectively brings the effective order of the integrator from 2nd order to 5th, while barely changing the time it takes to run the program. The exact benefits of these correctors change drastically based on the simulation. For instance, for an Earth mass planet, a fifth order corrector is about all that you need. It brings the integrator up to fifth order and nothing more is needed. But for, say, Jupiter mass ones with a sun mass star, 11th order correctors are very helpful in this case. Beyond that, we also include what we earlier talked about called the lazy kernel. Essentially, this is how we've stated that we will only be using the correctors at the very beginning and the very end. This works because to really take our information and our data points, we only need it at the very end. So we can apply those correctors to the transformation at the end to get our traditional physical coordinates that we can understand. But until then, it can be these change coordinates that don't really match physically, but match mathematically. This is important because rather than doing these symplectic integrators at each individual step 2 times, which would add high computational cost, we can do it just 2 times, which has a very low comparable computational cost, especially when going on for millions or billions of iterations. Now that we have all of this mathematical building blocks, we're now actually going to build this code. Taking this optimization problem to heart, I use Fortran, a computational science coding language that is quite old but very fast. Optimize, it's comparable and arguably faster than Optimize C++. It also has the added benefit of being much easier to read than traditional C++. I found papers that derived the best ways to optimize the subcalculations, specifically coordinate transformations, such as from Jacobi to Cartesian, as in this equation, you need to use both Jacobi and Cartesian coordinate systems a whole lot, and that is one of the biggest computational costs in the entire program is switching between them, as different Hamiltonians and their counterparts have different needs as the coordinates change. I won't bore you with all the details, but eventually I compiled about 15 of the most massive bodies that orbit the Sun. The 8 traditional planets, Ceres, Pluto, Haumea, Makemake, Gonggong, and Eris. Yes, Makemake and Gonggong are real names for dwarf planets. Now, as mentioned earlier in this video, I did not add moons to the simulation because of the nature of the Keplerian Hamiltonian. This wouldn't change much, but for instance, with the Earth and the Moon, where they have comparable masses, this could change things, especially as our simulation, which goes all the way up to about 900 million years, this could change things. Though that doesn't affect anything for our purpose of having a fun project that is mathematically challenging. If we were to take another system that we created random numbers for that just simply didn't have any moons, it would be perfectly accurate and it would work for it physically. I only use the planets in our solar system for the purpose of making sure that I have the numbers already set and don't have to make them up on the go. After this, to further increase efficiency, I set the time step to roughly 18 days. This is the max speed while still being accurate. Now we get on to the fruits of our labor. I really should have worked on another program to compare the two, as the numbers are mostly meaningless on their own. But as you can clearly see, these are very efficient results regardless. And anyways, the purpose of this was the process, not the results. Now that we have that, we can look at the results in a clearer way through an animation. So let's watch that.